Hello, welcome back to our machine learning course, and now we'll learn about sequence-to-sequence models. And the main problem we're going to solve is that the previous models we all discussed were back-of-words models, so they don't give information about the order of the words that come in. And so if the order is important, we're going to need a different type of model to deal with that. And this is basically the sequence-to-sequence model. This is a model where tokens come in the order of time, and it also outputs then a sequence of tokens, right? And in between something happens, so there's different ways of doing that. But overall, the model is such that a sequence of tokens comes in and a sequence of tokens comes out, right? It doesn't have to be a full sequence, so it can also be a label to sequence model. So here you can give a label like, I don't know, like a sorting algorithm, and then as input, and the output could be actual code that implements a sorting algorithm, right? Sequence to label could be, a sequence could be a review, and the label could be positive or negative. Or sequence to sequence, where you have a sequence in and a sequence out. For instance, you could have English text in and French text out. Right? And then you have autoregressive models, which are models which only predict the next output character or token, right? Like an autocomplete function. You would look at your previous sentence and then try to predict what the next word in your sentence will be. Right? There's different ways of building them, and we'll talk about a few possibilities. So the first of all is a 1D convolutional network. This is very similar as we saw before with 2D convolutions. This is just 1D. And so we can look at how this looks for our example here. So say that we have some input text. For instance, it could be a sentence like this movie number was not so, right? Just a sequence of words, right? Now we're going to, again, embed the words that come in. We get tokens in, and then what we're going to do, we're going to run a kernel across every token that comes in, right? So if we have an input token, we're going to run this simple 1/3 kernel. We're going to run it over the input, and out will come another another token or series of outputs that's changed by the kernel. And so this means that the kernel can learn different things, and you can have multiple kernels, of course, right? Every kernel learns a certain thing, and if a kernel has learned something in the beginning of a sequence, it can then also detect it later in the sequence if it occurs again, right? And then it will output values accordingly. Right? So in this case, we have one kernel. We run this over this the tree. So we have a tree, and then the next step is this. Next step is this. You get 3 outputs, and you get 3 output tokens, right? The next thing we can do is we can have another kernel of 3 values next, and then we combine those into one new output, and then we get this situation here with 2 layers, right? And we can have 3 or more layers. Now what you will see is that first of all, the memory is limited. I can only go so many steps to the right. So for this token to see an input, which is, I don't know, like 100 values to the right, it will never see that. It can only look 2 steps back, right? So it's limited in the memory. It can only look so many places for the backward. You can do things like multiple layers, you can add dilations and so on, but this intrinsic limitation that with the convolution you can only have so much memory, you can only look so far back into the sentence. Another thing is that this convolution actually, if you think about it, it's looking forward and it's looking backward in this sentence, and this may not be what you want. If you want to predict the next word, for instance, you should not be able to look forward. And so there we have special versions of this called causal convolutions, which means we're going to basically set these values all to 0. So we're going to ignore that part, and we can only going to look to the left of the convolution. Yeah, and these are known as causal models. By the way, there's no relationship with causality. They don't learn causality. They're just called causal because they can only look backwards in time. Right. We can implement this very easily. There's just conf1d. So I can take my input words, I can push them through an embedding. So I get my embedded words, my embedded tokens, these guys here in red. One convolution layer, ReLU, max pool, convolution layer, ReLU, average pool, flat and linear, and so now I can start predicting whether the review was positive or negative, for instance. A much more powerful solution are recurrent neural networks, which are very, very simple. They look like this. Internally, there's lots of interesting things going on, but on a high level, it's a very simple network where tokens come in. Again, this could be a movie review, like this movie was not, right? We take a token in, movie, we feed it through our hidden layer, and then we have an output, depending on what the hidden layer does. So we're going to train this. And then we're going to take the output and we're going to feed that back. We're going to concat that to my new input, right? So next time I'll have the word, so if this is the word movie, then previously we had the output for the word this. And we're going to actually put that back in, which means that my model now knows I have the word movie and the previous word was this or some output related to this, right? And you can imagine that this way this model can look infinitely far back into the future as long as it's remembering that word as part of the output, so that the next time it gets the input, it gets this whole history of words back. So the actual input of this is going to be the weight matrix that we learned times the new input times the previous output, so the bias. We're going to put it to softmax, and we can then learn this. And we're going to learn this doing something called backpropagation through time. We're going to feed a number of sentences to the network. Say this movie was not too terrible. And the label is, well, say it's positive, right? So what's going to happen? We're going to do cycles, 1, 2, 3, 4, 5, 6 cycles. Then we get a label, and then we're going to backpropagate through time. We're going to, in this case, unroll this model. So we'll have here again this movie was not too terrible. And so I'm still dealing with this one layer. I'm just going to unroll this through time, if you can imagine this, right? And this was the situation. So what I have here is the situation we have here, right? And this was a previous situation when we were inputting the word to this, sorry. And this is going to be the next situation when we would input the word was. And every time the output we had for this goes into my new situation, new state, where the new input is movie, right? And then the output of movie goes back into the next iteration where we encounter the word was, and so on, right? Every time we also have an output. And then we keep doing this until we have some signal back. So at some point we hit the word, we have a class positive. So, and then we well, we have a prediction, and then we compute the loss, and then we're going to back propagate that loss through all the layers, and then we can update the weights of a model. Okay, now you might already suggest feel that doing all these steps, this might lead to vanishing gradients, and indeed this is very, very common in RNNs that in principle you have infinite memory, you can go infinitely backwards, but you'll have huge vanishing gradients. So the practical memory is still limited, and it's going to be the downfall of RNNs. And people for a long time have, these are still used a lot, right? Models like LSTMs and grooves, they try to reduce the vanishing gradients through something called gating. So in an LSTM node here, what's going to happen? So we're going to have our inputs, and we're first of all going to have a hidden state as well, and we're going to have what's called the forget gate. And the forget gate is a simple, small network that's going to decide whether it's what it's going to remember from the previous inputs. Right? And the next, this hidden state goes together with the input. It goes into the forget gate. This is stored into what's called the internal state, typically called C, right? And then the same information goes to the next gate, which is the input gate. And the input gate is going to decide, okay, what are we going to do with this input? And then we also have an output gate, which is going to decide what we're going to output eventually. Right, and this C I plus 1 and H I plus 1, and so we keep iterating over this. And so the forget gate, input gate, the output gate, they're all trainable. They all have their own little weight matrix. And so as we back propagate through time, this forget gate is going to learn what to forget, right? So if it did forget something and it gets a high loss, then it will learn not to forget that much, and vice versa. Okay. Those are RNNs. Very useful. They're still used a lot, like LSTMs, or have still many good applications, but they still have this memory limit that we want to solve. And we're going to solve it with something called self-attention. Okay, now it gets interesting. So self-attention in principle is a very simple operation that maps a set of inputs again, like this movie was not too terrible, to a set of outputs. But so far, we are not going to include any weights yet. It's the self-attention operation in itself does something very simple. It's going to take all of our inputs, like this movie was, and so on, and we're going to compare it with all the other words in the same context window. We've fixed context window of tokens we're going to view, and we're going to compare every word with all the other words in the same context window, right? So if you have the word was at some point, the output of the word was is defined by the dot products of the word this movie was, yeah, and all the other ones. So we take the embedding for the word was, this is was again, this is was again, to this movie. And so here we take the dot product of the word was and was. Here we take the dot product of the word was and movie. Here we take the dot product of the word was and this, right? And so the dot product is gonna, well, on a high level, is going to tell me, okay, how similar is the word was to the word was? It's going to be high, or how similar is the word movie to the word was? And if the words are sort of similar as expressed by the dot product, then we'll get a high weight here, and we'll do it for all the words in the input context, and we're going to weight all the inputs by the dot products, and that's going to contribute a little bit to the output. So the output is going to be influenced definitely by the input word was, because the dot product by itself is going to be pretty high. It's going to be the highest value probably. And also by other words that have that are similar to the words that you put in. Was, say not two, so maybe this dot product was and two, sorry, was and two is high, so this also will have a large input into the output, impact for the output. Okay, so basically that's what we do. So we're going to take our input and we're going to blend it a bit with all the other words in the context according to the dot product of this vector and any other vector. Okay. So far this is not making a lot of sense, I understand that. Later on we'll see how we can make the dot product actually mean something interesting that we can really use. But so far we're just taking dot products between vectors and every other vector in the input sequence. Okay, this whole operation, while it seems complex, is actually a very easy operation where we take the weight matrix. The weight matrix are all the dot products, right? So we can just construct that. So given x, I can compute all the dot products, and then I have w. And then to get y, I just need to multiply w with x transpose, and this will give me y. And that's all I do. Yeah, and to compute the dot product, I can just do xtx, and then, sorry, I have to do it through softmax, of course, and that's my w. Those are my weights. But I'm not learning those weights just follow naturally out of my inputs directly. Okay, so like I said, what we've learned so far is that every output depends on every input, and we're going to mix that with the information on from all the other input vectors in the same context. Right. This way, W is going to tell us how much attention we're going to give to the other tokens, right? So if the weight is high, this other token is going to influence our output. So we can give more attention to that particular token. Maybe this one is also has a high dot product, means we give more attention to this token as well, right? So our output depends on our input plus the other tokens where we give a lot of attention to. Like I said, so far we aren't learning anything. There's no parameters yet. And basically all the information is inside the embeddings. If the embeddings are different, then we can do useful things with this simple operation, right? So the learning will actually happen by having multiple layers of these self-attention layers, and every time, so we start with simple word embeddings. We'll get output tokens, and next layer again output tokens, and the way that these tokens change through the layers, that will actually define what the output of the next layer will be. what you should probably notice is that we're not doing anything fancy, and we can look very back into the sequence, right? This is one simple matrix operation. So if as long as my W is large, let's say it's like, I know, like 1,000 by 1,000, then I am able to look 1,000 words back into the past, and it doesn't cost me anything, right? Well, I need to store this big matrix, but I'm not losing. There's no there's no gradients to vanish really, so I can look very far back into the sequence. Also note that I'm operating on sets, so whether the sentence is "this movie was not too terrible" or "this cat was not too pink." Oh, sorry, what I'm saying. So whether the sorry again. So whether the sentence is "this movie was not too terrible" or "this terrible movie was not too," that wouldn't affect the output at all, right? Because I'm just summing everything up here. So there's still no ordering that I'm actually using yet so far, right? So it's actually a set operation. I have a set of tokens in and I get a set of tokens out, which also makes it very flexible. I can use this for all kinds of things like image to set, set tasks, and so on. Yeah. So if the order matters, we'll have to add something to make it matter, and we'll see that in a few slides. Okay. So first of all, self-attention is very powerful because it's mostly a linear operation, right? It's exactly a linear operation between this weight matrix and the input x. It's linear, and there are no vanishing gradients in this, right? The softmax function only applies to w, and w is again xtx, and then we have some vanishing gradients because we have a softmax here, but still it's very little. And we still need the softmax, of course, to make sure that the attention value sum up to 1 without exploding. The dot products, by the way, they do get larger as the embedding dimension k gets larger. And so to solve that, we're going to normalize this by a factor root of k, k being the dimension of the embedding. Right? And this also makes training more stable, right? Because large softmax values tend to lead to very sharp outputs, right? If you can remember that, but if you would plot a softmax, it would look a bit like this, where high values get higher values, and this is nice if you have like 10 classes, but if you have 1,000 classes, then this will be an extremely sharp curve. Actually, it's a piecewise linear combination anyway, which means that only if you will have any meaningful weight, all the rest will be basically 0. And so to solve that, we do this weighing factor, which will help us avoid that. This is why we scale the dot products. Okay, now we can complete a model, right? So I have my example again. This movie was not terrible. I feed this to my embedding layer. This could exactly be glove, right? You can choose whatever embedding you want. Nowadays we have subtoken embeddings, whatever. Outcome the embedding tokens. Then we have our simple subattention layer. From that we get our output sequences. We then do global average pooling to get outputs. Then we have our dense layer, and here we output. And then we have a loss, and then we can use that loss to update my dense matrix, and so forth. That's all I can do, right? In the next step, we'll actually also use this to update something in my self-attention layer that I haven't introduced yet. Okay. Right. Okay. Now, remember that we want to be able to learn negations like terrible and not, right? So not and terrible should ideally have a high output so that the occurrence of the word not will have a big influence in the output of the word terrible, right? So we need to learn to change the representation of the vectors not and terrible so that this dot product is going to be high. And so to do that, we will actually have to introduce some trainable parameters. And we're going to do that through three matrices, K, Q, and V. K stands for key, Q for query, and V for value. And we'll explain in a second what that means. But just to show you how we introduce those matrices, so we're actually going to create these matrices. They will have the dimensionality of our input vectors. So if our input vectors are 300 large, it's going to be 300 by 300 matrix, but the size will depend how deep we are in the architecture. And we're going to have three different matrices. Not one per input, but one per role in this operation. One the value, one the key, and one the query. Okay. And so these are going to be trained so that we change the inputs in such a way that we're going to learn something useful. So depending on whether we are dealing with the input token, so the token we're currently inputting, the token we are currently looking at, which is again the same token but then transformed differently by the Q matrix, and the other token we're comparing with. Right. And so to illustrate that, so first let me explain where this terminology comes from. So the word key, query, and value, as you may remember, comes from the world of dictionaries. So imagine you have a dictionary S with keys A, B, and C, and values VA, VB, and VC. Now normally if you do a query, you would have dictionary S, you would have a query C, and the answer to the query will be the value corresponding to the key C, right? Now, if you have a soft dictionary, this is a special dictionary where every output, every value has some weight, and the weight depends on how close the key is to the query, right? And we're going to solve it with dot products, right? So our output of my soft dictionary is going to be the dot product of every key with my query times their out value. And if you see, this is exactly what's happening here. So I take my value C, I have my key C, and I have my query C. The query C will always be the same, so I'm going to check for every possible other vector in my other token in my context. I'm going to see how well do I resonate with that, right? I'm going to do it with KC, with KB, with KA. If those resonate well, then I will get a high dot product here, and then this value will have a bigger influence for my output, right? Now, what are we looking for? We're looking for any relationship between the tokens. And to give you one example, like remember we were interested in being able to handle the word not. You can imagine that there is at least one version of this Q matrix which learns to look up negations, right? So in this case I have the word terrible. Then basically what I'm doing is I'm going to query every other token in my context I'm going to ask it, are you a negation? Are you a negation? Are you a negation? Right? And then the answer will depend on how the K matrix has adapted this input. So if the word here is not, and then the K matrix should learn how to respond positively if not is a negation of the word terrible, right? So the query matrix here is going to learn how to convert my input terrible here into the question, is this a negation of terrible? While the K matrix here will learn to respond positively if the word not is a negation for the word we're comparing with. Right? And so in this case, not should actually respond strongly to the query whether this is a negation. Yes, and then this not will have a big influence on the output. Right? And so you would actually have to learn different Q matrices to learn different relationships, right? So this Q matrix here, which learns to basically query for negation, can only do that. It can learn this for a negation for terrible or a negation for any other query, that's fine, but it can't learn something very different like, is this the color of, right? It cannot do that. So I would need to learn another Q matrix to answer a query or about, for instance, is this the color of, right? All right, good. All right, like I said, a single Q matrix can only learn to ask a simple query like an inversion, but you can also have a moderation, like 2 will moderate terrible. And terrible is a property of the word movie, right? If I want to learn those relationships, in principle, I would have to create a single self-attention layer for every possible relationship that we want to learn. That's a bit expensive, but we can do a little trick called multi-head self-attention. And that basically works by having basically multiple Q, K, and V matrices in parallel. And we're going to solve that not by creating 4 attention matrices layers, but we're going to divide our input vectors into 4 smaller ones by just doing a lower dimensional mapping from our original one to our 4 different smaller representations, right? So if this is a 300 dimensional vector, then maybe these are it's not divisible, not really divisible, but just say this is 50, 50, 50, and say this is 200 to make it easy. Okay, so we do a projection from a 200-dimensional vector to 4 50-dimensional vectors. For each of these, I'm going to learn a K, a Q, and a V matrix so that I can, for instance, look for 4 different types of queries in parallel. I can learn 4 types of relationships within the same attention layer. I run those in parallel, and at the end I get the outputs. I'm going to concatenate them again to get the outputs of the same dimensionality again here out. Right? That's multi-head self-attention. It's a simple trick that allows me to learn multiple relationships between the tokens in parallel. Okay, that's it. In the next lecture, we'll talk about transformer models.